Welcome back, students. Let's look at resonance and how it relates to delocalization. First, I want to remind us what localized versus delocalized means. A delocalized lone pair is something that participates in resonance. It's something that is shared over multiple atoms. Whereas localized lone pairs do not participate in resonance, and thus they live solely on one atom. In an earlier video, we talked about how localized and delocalized is a set of terms that can be used with respect to painkillers. So for example, if you're still struggling with localized or delocalized, think about a localized painkiller. You know, you hurt yourself in one area of your body, maybe you need to get a tooth out, and you get a localized anesthetic, and they just numb that particular area. Whereas something that would be delocalized would go throughout your entire body. Now let's look at how this is going to play out in chemistry. In chemistry, this is showing a localized lone pair. And here, this one is delocalized. It is really important that you've had tons of practice with drawing resonance structures so that when you are drawing resonance structures and you draw the arrows to generate more resonance structures, you're not drawing the arrows wrong. Otherwise, when you come into questions like this, where I'm saying, hey, this lone pair is localized, whereas this lone pair is delocalized, if you're not drawing your arrows correctly, you can make any pair look delocalized, and it's not. Now let's talk about why that first pair is localized. That first pair is localized because it lives solely on that nitrogen. There's no other atoms that it can be shared over. The second structure, the pair is delocalized because one atom away, you have a pi bond. Remember, your pi bonds are created from overlapping p-orbitals. So a delocalized lone pair is also living in a p orbital. And you have the ability to draw this set of arrows in order to generate another resonance structure that looks like this. And in this resonance structure, what we're doing is we're showing that the lone pair is really, and the pi bond, is really shared over multiple atoms. I want to highlight where those atoms are, right here, here, and here. All of those atoms have p orbitals on them. So there's a p orbital here, there's a p orbital here, and there's a p orbital here, and they're all sharing the electrons through that set of p orbitals. And that's what delocalization is. The question then ends up being, how does this impact hybridization? Because your electron pairs are delocalized and shared through p orbitals, it's going to update some of your ideas about hybridization. Before we get to the update, let's go back to our normal ideas about hybridization. I have the same structure redrawn here, and I'm looking at this lone pair. If you were in general chemistry, what would you say the hybridization is of that nitrogen? And that nitrogen has 1, 2, 3, 4 electron domains, and therefore is sp3 hybridized. One thing that I find is that students will know how to determine what the hybridization of an atom is, but they don't really know what it means, because that lone pair, it actually lives in an sp3 hybridized orbital. Right? It is on that nitrogen. It's not shared over here. It's not shared over here. It is living on or in an sp3 hybridized orbital on that nitrogen. So when I say what orbital does that lone pair live in, you look at the hybridization of that atom, and whatever the hybridization of that atom is where that lone pair is living. And then the bonds are created between the sp3 hybridized nitrogen and another atom's particular orbital. So we went back to general chemistry. We said in general chemistry, we would have looked at this and said 4 electron domains, and that means sp3 hybrid. Let's change it up. Let's change it to the structure that we had earlier, where we have a pi bond there now. We said that that lone pair is now delocalized in this structure. But what does that mean for hybridization? If you went back to general chemistry, what you would do is you'd look at this and say 1, 2, 3, 4 electron domains, that must be sp3 hybridized. But the nitrogen is not sp3 hybridized in here. It can't be. And why can't it be? Because you said with me on the prior page that the electron pair here is delocalized, which means it's shared through a series of p orbitals. If it's shared through a series of p orbitals, then how did we use the p orbital to get hybridized, and now the p orbital is not there anymore? The p orbital still needs to be there. Whenever anything is delocalized, that electron pair is living in a p orbital. So delocalized pairs of electrons live in p orbitals. When I look at that nitrogen, one of the things to help me see that we have a sp2 hybrid orbital for that nitrogen is to successfully draw what we did on the prior page. Draw its resonance structure. And when we draw that resonance structure and we end up looking at the nitrogen now, I'm going to highlight the nitrogen. Now that nitrogen certainly looks like it's sp2 hybridized. And it can't be both. It can't be one or the other. Because we know that delocalized lone pairs live in p orbitals, this is representing the hybridization of the nitrogen. Because that lone pair and the pair in the double bond are being shared over 3 total atoms. Now, in Organic Chemistry 1, we just introduced you to this. I want to give you a little bit more practice and another example. At the same time, I don't want you to freak out if it doesn't make a whole lot of sense yet. Because once we get into Organic Chemistry 2, we'll really dive into it when we get into aromatic compounds. I just don't want you, I don't want to lie to you because I know that's tough when you find out later that your teacher withheld information because you weren't ready for it yet. So this is sp2 hybridized, and that lone pair lives in a p orbital. So here the lone pair is shared in a p orbital. Let's look at another example. Here I drew you a set of resonance structures, and I want you to look at the nitrogen and figure out what the hybridization of the nitrogen is. You can go ahead and pause me and think about it for a minute, and then we're going to come back and look at it together. All right, I'm curious to hear what you came up with. If we look at the nitrogen here, again, this one certainly looks like it's sp3 hybridized because it has 4 electron domains. Remember that electron domains are just groups of electrons around the atom that you're considering, and we count them as attached atoms and lone pairs. We see that nitrogen has 3 atoms attached in 1 lone pair. It has 4 electron domains, and in order to satisfy the 4 electron domains, it needs an S, a P, and a P. Hybridize them all together, blend them up, and you get sp3 hybrid orbitals. But then the problem is over here, the nitrogen certainly looks different Now, instead of having a lone pair on the nitrogen, you have that double bond, and this is going to be an sp2 hybridization. And it can't be both. It's not flip-flopping. There's no movement. Remember, we talked about how the biggest misconception in resonance is people think that this structure is existing one moment and this structure is existing the next moment, and that is false. What's actually existing is a blend of these structures, which is the resonance hybrid. So if we're looking at hybridization of that nitrogen, it can't be sp3 hybridized and sp2 hybridized. So the easy way to go about this is pick the lower hybridization, because that's what is actually happening. But I want you to have a deeper understanding than that. I want you to recognize that the reason that the nitrogen has to be an sp2 hybridization is because your nitrogen has a pair of electrons that's being shared over multiple atoms. And you can only have that sharing when you're in a p system, where one atom has a p orbital and the next atom has a p orbital that's parallel to it, and the next atom has a p orbital that's parallel to it, and they're all sharing through the whole thing. So what is the hybridization of the nitrogen? It is sp2 hybridized. I have one more question that I want to work on. And this one, I drew the structure on the left for a molecule called pyridine. And I want to look at the lone pair on the nitrogen and try to determine if that lone pair is one that is localized. So does it live on the nitrogen? Or is it delocalized, meaning is it shared throughout the entire ring? And here's where we really need to know our arrow pushing patterns. If you don't know your arrow pushing patterns, you can certainly come up with all kinds of resonance structures for pyridine, but they won't be correct. This is one idea that's a little bit new. One thing that we haven't talked about yet is when you have a pi bond and then a lone pair on the atom that's involved in the pi bond. Off to the right-hand side, I have an orbital diagram picture of what pyridine looks like. What this is trying to illustrate is each of these pink orbitals are unhybridized p orbitals on each of the carbons. Remember that each orbital has one electron that it's sharing to make a bond, and that's why there's one black dot in each of those unhybridized p orbitals. When we're looking at this carbon, it is sp2 hybridized, so it has one p orbital that didn't get hybridized, and that's the one that's involved in creating the pi bond. The other thing that this is showing is all of my p orbitals are all parallel to one another, which means they can all overlap. And they're actually overlapping above the ring and below the ring. It's just hard to draw both of them and have you still be able to see it. Now let's focus on the lone pair. The lone pair cannot be in one of the p orbitals. Because the nitrogen is involved in a double bond, the double bond is using the p orbitals to be created. So this p orbital right here, that's being used to create the nitrogen-nitrogen double bond. So here's the rule. When you have a lone pair, so when there is a lone pair on an atom where that atom is involved in a bond, the lone pair is localized. The only way for that lone pair to have been delocalized is if it was part of that p orbital system. but you already have a p orbital that's being used to make a pi bond. And because that p orbital is being used to make a pi bond, you can't have another parallel p orbital on the same atom that has the lone pair in it. It's just not possible. Because remember, the p orbitals are 90 degrees apart from one another anyway. So even if that lone pair, which is here, was in a p orbital, it still couldn't be delocalized through that parallel pi system. Now, if you're looking at this going, whoa, this was too much. I hear you and I know. And again, this is kind of just a little bit of a, hey, hybridization wasn't as easy as you thought it was going to be, to get you ready for deeper conversations in the future. Especially if you end up taking organic chemistry 2, you're going to dive a lot into this when you start talking about a concept called aromaticity. Let's wrap up. At this point, what you want to do is you want to be able to understand the difference between a delocalized and a localized lone pair. Even just being able to understand that a localized lone pair lives on an atom and a delocalized lone pair is shared over multiple atoms is going to be a big thing. I want you to know that hybridization is affected by delocalization, but if you're in my class, we're going to save most of those ideas about what the hybridization actually is and predicting if a lone pair is delocalized or localized in the difficult examples for Orgo 2. For right now, in very basic resonance structures, you should be able to look at a lone pair and decide, is this lone pair localized or delocalized? As always, thanks for your attention. This is Katoni signing out.